Hello my dears, how are you all? So we started measurements, right? Yesterday we started measurements. So we did some error analysis and some problem regarding that, and we found the expression for the maximum error, right? Maximum error if it is in additive or subtractive manner, or if it is in division or multiplication manner. Anyway, you can directly find the error, correct? And you found a conclusion, or we found a conclusion, right? In case of addition or subtraction, the magnitude of errors can be directly added. In the case of addition or multiplication or division, the percentage of error can be added directly. So one is in percentage, that is multiplication or division, then there will be a percentage of error will be there. If not, you have to convert into percentage. And in addition or subtraction, the error will be in magnitude only, not in percentage, in magnitude only. If it is in percentage, you have to convert it into magnitude. That you have to take care of. Okay, that's all about the concept of error. So let's do one more problem, one or two problem regarding that, so that we will be strong. Okay, because that type of questions will be normally asked in examination. Okay, so let's do one more question. Let's do one more question. If the percentage error in the current flowing, if the percentage error in the current flowing through the conductor I will be equal to 100 plus or minus 10%, having a resistance R is equal to 10 plus or minus 20%. Find the magnitude of error in power. Find the magnitude of error in power. Listen. How can we do this? How can we do this? Listen, my dears. If the percentage error in the current flowing through the conductor, that is current is given, right? Current is given, having a resistance of R also given. Find the magnitude of error in the power is simple. It is very simple. Power P is nothing but, my dear, I square into R. So what is I here? So it is nothing but 100 plus 10% into 100 plus 10% into R. R is nothing but 10 plus 20%. It is plus or minus 20%. So yesterday we learned something that, what is that? If it is in multiplication or division, percentage of error can be added, correct? So you have to directly multiply this 100 into 10. So 10 raised to 2, 10 raised to 4 and 10 raised to 5. Am I correct? 10 raised to 5 plus or minus 10 plus, add this percentage, 20 plus 10, 30 and 40%. So 10 raised to 5 plus or minus 40% is a power. So we have to magnitude of error in power. Magnitude of error in power will be equal to what? 40%. So that is the answer. (20 plus 20, 40). Okay, so this will be the so this is the percentage error, correct? Magnitude of error will be simply what? 40% means 40 by 100 into magnitude will be 10 raised to 5. 4 into 10 raised to 4 into 10 raised to 4. Okay. So this will be the magnitude of error. Magnitude of error in power. 4 into 10 raised to 4. %, yes. Okay. Is it clear, my dears? Is it clear? Okay. And let's see the next question. 10 plus 10, 20, 22 is 40. 22 by, correct. 22 by 1. Okay. Magnitude of error in power, am I correct? Just a minute, my dears. Just a minute. Yeah. Correct. Okay. So that is the magnitude of error. Magnitude of error in the power. So plus or minus this may be varying. Am I correct? Plus or minus this much may be varying. This much watts may be varying. Okay. That's all. So write another question. It's very easy, right? It's very easy. Just a simple multiplication. Okay. Write another question. If a voltage is applied on a conductor, if a voltage is applied on a conductor, V is equal to 100 plus or minus 2%. The conductor is having a resistance of R is equal to 100 plus or minus 3%. Find the magnitude of error in power. Magnitude of error in power. Magnitude of error in, listen my dear. If a voltage is applied on a conductor, V is given, so R is also given, right? V is given and R is also given. Then what is the power equation, my dear? Power P is nothing but what is that? V square by R. So it is nothing but 100 plus or minus 2% into 100 plus or minus 2% whole divided by R. R is nothing but 100 plus or minus 3%. So the division will be 10 raised to 4 divided by 10 raised to 2 into, here it will be 10 raised to 4, multiply this, add this, correct? Plus or minus 4 divided by division means what is that? 10 raised to 2 plus or minus 3%, correct? So it will become, normal division will be there for magnitudes. So it will be what, my dear? 10 raised to 2, right? 4 by 2 will 10 raised to 2 plus or minus, add this percentage, correct? So 7%. Okay, this is the total power. This is the total power, which means magnitude of error, this is in percentage. We have to magnitude, right, means 10 raised to plus or minus 7% means 7 by 100 of what? 100. So 7. So it will be 100 plus or minus 7 will be the magnitude of power. That means plus or minus 7 watt may be varying. So magnitude of error is equal to plus or minus 7 watt. Plus or minus 7 watts may be varying from 100. 100 plus 7 or 100 minus 7. Both can be added. So magnitude of error will be simply 7 plus or minus 7 watts. Is it clear, my dears? Is it clear? Okay. So that's all for that question. Is it clear? Listen. Next, resolution. Resolution means, if you heard the term resolution, it is the smallest division seen by naked eyes. Smallest division of scale seen by naked eyes. For example, if you consider a scale, my dears, it's a 0 to 15 centimeter scale. You consider 15 centimeter scale. So it will be like what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 10. Like 15s will be there, right? Like 15 will be there. So the resolution definition is that the equation for finding the resolution is that resolution is equal to, my dear, full scale deflection divided by total number of divisions. Full scale deflection here it is what? 15 centimeter. So 15 divided by total number of division will be, my dears, 15 into 10. Am I correct? Total 15 will be, each centimeter consists of smallest 10 division. Correct? So the smallest number of what division you can see is nothing but what? 0.1. That means it is equal to 1 millimeter. Am I correct? 1 millimeter you can see by your naked eyes. So it is the smallest division in the scale. It is the smallest division of the scale naked by the what? Eyes. Naked by our eyes is called the resolution, or the capacity of resolution. Am I correct? Am I correct? So full scale deflection divided by smallest resolution, we will give the value like 0.1. Am I correct? 1 by 10 is equal to 0.1, which means 0.1 in terms of what? Centimeter. 0.1 centimeter is the smallest division you can see by your naked eyes. That is called the resolution. That is called a resolution. Okay. So high resolution means what is the meaning of high resolution? The smallest will be very, you can separate the content by using, for example, suppose you are seeing an HD movie. HD movie is very high resolution movie. Okay, suppose 1080 pixels. 1080 pixel movie, and other one is 480 pixel movie. Which having highest resolution? This having highest resolution. Highest resolution. Am I correct? What is the meaning of that? In every content, my dears, in every small content, every small cell, you can see 1080 dots for fulfilling that particular image or particular scene or particular frame. That means, suppose you take 1 centimeter here, 1 centimeter length and 1 centimeter height. So length into height 1 centimeter. So 1 centimeter square area you are considering. Suppose it contains 480 dots. It contains 1080 dots. 1080 number of dots it will contain for 1 centimeter square, which means the content rich or the quality of the content it is seen. Suppose your face, my dear, your face, suppose you are a face. In children are playing with some arrangement like structure. Did you see that? That means there will be a structure of an apple. Suppose this is an apple, my dear. Suppose this is an apple. They are playing with the structure like, did you see that? This is divided into small groups like this, and we have to join it, and it will get a full figure. So if the number of pieces are very high means, if the number of pieces are very high means, if you join it together, you will get a crisp image. Actually, did you get my idea what I am saying? Here, 1 centimeter square contains 480 contents. Rest all are noises. Rest all are noises. Correct. Suppose you have to fill it with the 480 balloons, means each balloon will be some size, right? Suppose here you have to fill the same area with the 1080 balloons, means it will be what? Smallest balloon will be there, so that you can even see a minute curvature. You can see a minute change in the figure. You can see a minute change in the figure, or you can feel the every detail of that figure if the resolution is very high. That's all simple. High resolution microscope. What is the meaning? You can move into very deep level of every small organism or every cell and all. That is the meaning of high resolution. Okay, that's it. So you will get definitely. It is enough. So the equation you have to remember, it is full scale deflection divided by total number of division parts. Full scale deflection divided by total number of division. That's all. Okay, my dear. So that is the meaning of resolution. That is the meaning of resolution. Is it clear, my dears? Is it clear? Next, types of torque in measurement or indicating instrument. Listen, my dears, listen. So there are 3 types of torques. First one, deflecting torque. It is represented by, my dears, TD. It is just a minute, I will refill my pen. Okay. Okay, so deflecting torque TD. So what is the meaning of deflecting torque, my dears? Deflecting torque. Suppose you consider a pointer like this. Suppose this is the scale. You consider this is the scale of an instrument. So this is the scale, my dear, 0 to 10 or 0 to 5. 0 to, suppose it is 5. Okay, 0 to 4. 1, 2, 3, 4, correct? 0 to 4. There will be a pointer, correct? And there will be a pointer like the structure. So deflecting torque means it is the torque responsible for the reading, or it's the torque responsible for starting the pointer from its 0 position to the corresponding value of what voltage or current applied. Or the deflecting torque means it is the torque required for the deflection of the pointer. Okay, that is the deflection of it. So I will say like this: it is the torque required for the pointer to start from its 0 position to corresponding voltage or current or power applied. Did you get the idea? Did you get the idea? So deflecting torque means it is the torque, it is a torque developed by the pointer has to start from the 0 and it has to move to corresponding value, correct? So that torque is called the deflecting torque, my dears. That torque is called the deflecting torque. Okay, so the deflecting torque now, this can be this torque can be generated by any method. For example, suppose you are placing your pointer in a magnetic field, my dears, in a magnetic field. So this magnetic field effect, this changing magnetic field effect will be a reason for this pointer to move, which is called the magnetic effect. Magnetic effect. Sometimes a chemical change may be the reason for the pointer to move from its 0 position. Then that type is called the chemical effect. Sometimes the temperature rise will be the reason for the pointer to move. Then it is called the thermal effect. Sometimes a small voltage generated may be the reason for the pointer to move. It is called thermocouple effect or thermoelectric effect. Thermocouple effect or thermoelectric effect or Hall effect, etc. or magnetic effect. That is already told, right? So this deflecting torque may be arised or it may be generated by any one of these reasons. Any one of these reasons may be the responsible factor for the deflecting torque. Is it clear? Is it clear? Which means it doesn't mean, see, any of the method can be applied. Here it is the current, the current will be the reason for the movement. In next case it may not be the current. Sometimes the pressure or the mechanical will be mechanical force, that may be the reason. Even the mechanical, suppose you are in future, not in future, in continuing classes, you may learn with mechanical, bellow process like arrangement you are going to learn. There the physical displacement itself will be the reason for the pointer to move. See, at that time mechanical effect will be there, right? So any of these effect can be utilized. Like in thermocouple effect, you learn that thermocouple, if two bodies are placed in there are two bodies which are in different temperature situation. Suppose you connect that two bodies with a wire, then there will be a flow of current from the hotter body to the cooler body. So that is the thermoelectric effect, Seebeck effect. You learned that Seebeck effect. So like that, many of the effect will be there in order to generate that type of deflecting torque, Okay. Next, it is called the control. So deflecting torque in terms of this deflecting torque may be, see my dear, deflecting torque in terms of this pointer. Suppose we are dealing with electrical measurement system, then the deflecting torque may be directly proportional to what, my dear? Deflecting torque may be directly proportional to, sometime it may be proportional to current, or sometime it may be proportional to I square, or any factor you may observe, like, okay, sometime it may be proportional to the current, sometime it may be proportional to current square, sometime it may be proportional to power, or anything you can assume. Not assume, you can get. So that is the concept of deflecting torque. Next, controlling torque. DC. So controlling torque, my dears, controlling torque, I will explain. It is the torque acts in opposite direction to the deflecting torque TD, to the TD, so that pointer can be stopped accurately in particular reading. Also, this is the torque responsible for the come back or return of pointer when the quantity to be measured is removed. Listen my dear, so controlling torque I will explain. Suppose this is a pointer, again you got a pointer like structure. This is our scale my dear, this is our scale. So you have to start the pointer from 0 to a particular value now. So definitely there will be a deflecting torque that I already told you. That is the responsible that is the torque responsible for start the pointer from 0. Okay, it started. If it is deflected means it will swing to at the extreme point end now. Suppose you take a carom board. You what the midiki you start hitting the carom board like this. That carom board, not carom board, it is caroms, correct? On the carom board. So you start kicking the caroms. It may not be stopped at what point you decided. It may move to some more distance away, right? It may move some more distance advanced, correct? So that advancement in the case of caroms, it is not that much problematic. But in the case of measurement, see, suppose you have to find a 5 ampere current media. This is up to 10 ampere, this is 0. Suppose you want to find 5 ampere. So the deflecting torque corresponding to 5 ampere may generate here and the pointer will start deflecting. But it may not be stopped at 5 ampere due to inertia because it's already in motion now. So it has the tendency to come much more distance. So to avoid that my dear, an opposing torque will be there inside this pointer, so that when deflecting torque advances or deflecting torque improves, correspondingly you have to oppose another torque. And at a steady state position my dear, at steady state position, the deflecting torque and the controlling torque should be equal. Then only we will get a corresponding reading. If any one of this is greater or less than, what happened? Suppose you TD greater than TC, what happened? The pointer again move. It won't get there. It won't but correctly stopped at that particular point. It may move a small distance again. Suppose TD less than TC means it may not reach at 5 ampere. It may stop before that 5 ampere. Yes. If TD less than TC, because TC is overcoming there. So controlling means it is opposing now. Controlling torque I already told you, it is an opposing torque. So opposition will be higher than the forward direction. So opposition will be higher means it may not be stop at 5 ampere. It may stop at 4 ampere. It may stop at 3.5 ampere or anything depending upon this quality, correct? So that is the meaning of controlling torque. So controlling torque means my dear, it is the torque responsible for the control purpose, correct? It is the torque responsible which is acting directly opposite to the deflecting torque, so that the pointer should be stopped at a corresponding point or corresponding current or corresponding mode or anything, corresponding quantity. You may say like this, corresponding quantity, the pointer should stop. So the torque responsible for that stopping, the torque responsible for that stopping of the pointer is called the controlling torque. If controlling torque is not there, suppose you apply a 5 ampere current, it may stop at 10 ampere, it may stop at the end, because end will be the stopping point, only end will be the stopping point. Even 2 ampere current you applied, it will end at the ending point, because only that there will be a permanent stop now, there will be only stop. So that is the problem. So there should be something to oppose the deflecting torque so that the pointer can be stopped at a correct point. Is it clear my dears? Is it clear? Is it clear? So there are two types of controlling torque. There are many types of controlling torque actually that we will discuss later. Okay, type of controlling torque we will discuss later. Now third type of torque is called damping torque. damping torque, my dear. So damping torque means damping torque, my dear, is nothing but it's the torque responsible for the damping of oscillation. Damping of oscillations of the pointer. I will tell you. So what we applied a deflecting torque so that the pointer can be started from its 0 point. The pointer can be started from 0 point, and due to controlling torque it may stop at somewhere. But at the point of stopping now, my dear, the deflecting torque and controlling torque now, it is an ideal case TD equal to TC, okay, it will stop. But practically at this point, the stopping instant, the stopping point, the pointer cannot stop immediately, my dear. The pointer cannot stop immediately. It will slowly oscillating and oscillating and oscillating, slowly oscillating. Then only it will stop. It will oscillate to the final position, so slowly oscillate, and then stop. Is that appreciable or favorable? No, because we need a reading. So as soon as possible, we need a reading. Suppose it is a temperature rise of a steam engine or something like. Suppose this is oscillating, you are continuously measuring. What is the temperature? At that time, the burst may be happen. At that time, within that time, the burst may happen. So that's not appreciable, my dear. So we have accurate reading, a quick reading. So the damping torque acts there in order to suppress that oscillation, or in order to damping of the oscillation produced by the pointer. We are using the damping torque. Is it clear, my dears? Is it clear? Is it clear? Is it clear? Next, you have to see two type of controlling torque. That is controlling torque. Types of controlling torque. Measurement is somewhat theory, my dears. Problems also there. Theory is also there. Types of controlling torque. Types of controlling torque. Listen, there are two types of controlling. One is spring control and is gravity control. Spring control and gravity control. Okay. So what is mean by spring control? Let's see first spring control. In spring control, my dears, spring control. So this is the controlling torque now. So in spring control, there are two types of springs you are using. Springs may be helical type or spiral type. Helical means, my dear, this is the case. So this is the helical case, and spiral means this is the case of spiral. So these are the two types of springs. Any springs you can use for the control purpose. It is for control purpose. So spring control, what is the nature? So in spring control, the controlling torque, my dear, is equal to k theta. It is very, very important. In spring control, the controlling torque will be equal to k theta, where theta is nothing but the deflecting angle and k is nothing but the spring constant. Theta is nothing but the deflecting angle, and this k is nothing but the spring constant. K is nothing but the spring constant. Or I can say that the controlling torque is Tc proportional to theta. Tc proportional to theta. So only this relation you have to remember this. Next, the properties of the spring. I mean, in spring control mechanism, this spring maybe the reason for the, I mean, this may be act as the leading of the current entering and the current outgoing from the instrument and to the instrument. It may acting sometime also, that we will learn when we are learning particular instrument. Okay, so as of now it's enough. So the properties of spring. What are the properties of a good spring by using its spring control method? First one, it is non-magnetic. Second one, it's non-corrosive. Third one, high mechanical strength. High mechanical strength. And fourth one, low alpha. What is alpha? Temperature coefficient of resistance. And fifth one, low temperature coefficient of expansion. So these are the properties of the water. Properties of a good spring. So the material which is act as a very good spring is nothing but phosphor bonds. This is the best material for using the spring control. I mean spring for the spring control method. Okay, the material is phosphor bonds. Or there are other material also. It is beryllium copper. This is also very good material for spring control. I mean spring control. Yes, spring control. Okay, so that are the properties of a spring in order to make it use as a spring control or controlling torque. Is it clear? Is it clear, my dears? Any method, any of the spring can be used. Normally we are using this type of what? Spiral spring, my dears. Spiral spring. Okay. Next. Today RRR movie released. I am very thrilled of that. I booked a ticket for Monday. Definitely we will go. So it will be an amazing movie. Definitely. Definitely I will. I am very thrilled. Okay. I can't control my thrilling. That's why I am sharing with you. Okay. So you must go and watch in theaters. Possible, if possible, in 3D. Okay. It will be a next level experience. Next is come to our point, my dears. Gravity control. Gravity control. Actually, when I was a teacher, I mean, for a long time, for 8 to 9 years, I took classes for BTech as well as MTech students. So at that time, now I made a small break for my personal reasons, and after 6 months again I will join. Okay, so now I had a break. I'm in a break. Okay. So at that time I remember still what I did normally when I took a long classes. This measurement also I took at that time. So at that time it was normally after lunch break. If you are a student, definitely you know that after lunch break is a really boring session. Even if Einstein take a class, you will sleep. You will sleep. Even Einstein take a class, you will sleep. So that was the time. Actually, after very heavy lunch, heavy lunch. Even if not a good, it not. Okay. So come back to our session, gravity control. So in gravity control, my dears, draw this figure. Listen, my dears. Suppose this is the mechanism of controlling torque. That means this is the pointer, of course, this is the scale, you know that. There will be two weights, my dear, equal weight. This is the controlling weight and this is the balancing weight. So normally what we have, due to the center of, acceleration due to gravity, the controlling weight will be always acting downward. That G factor will be always pull the system to downward, pull the controlling weight to downward. Suppose we would apply some current or voltage, right? It will be the pointer definitely move from one point to another. That moving angle will be theta. That moving angle will be, my dear, theta. So due to this deflection, what happened? This control torque also move slightly in this direction. So this balancing weight also moving like this. So what happened, my dears? This G this will be again always act to the downward direction. That will bring, that G will bring the control weight to its original position again if the pointer, if the magnitude removed. That means the pointer should be at steady state now. At some time that reading should be noted so that it will be in steady state after some time. At a steady state, what, my dear, this controlling weight as well as balancing weight it balances each other. That TD is equal to TC condition is again applied here. Controlling torque will be equal to a balanced torque will be again, then only you will get a reading, of course. So this controlling is nothing but it will come here, so it also come down. So it is again slide to balance itself if you remove the quantity that we applied. Is it simple? Is it that much simple? No? It is that much simple, no issues there. Okay, and in gravity control, my dear, the controlling torque TC is equal to WL sin theta. It is actually a long derivation. You get this relation TEC is equal to WL sin theta, where TC is the controlling torque, W is the controlling weight, and L is the length of controlling weight. Okay, so this W and L will be a constant, my dear. It won't change with respect to time. So I can directly write TC proportional to theta. This is very, very, very important relation. You need not remember this relation, but you always remember this relation. In gravity control, the controlling torque TC will be directly proportional to sin theta, not sin theta. Directly proportional to sin theta. Is it clear, my dears? Is it clear? Okay, and listen, my dear, since TC proportional to sin theta, since TC proportional to sin theta, that is the controlling torque is directly proportional to single quantity, it is proportional to sin theta. So the scale of this instrument is not uniform, is not linear. Suppose in previous case, in this case of spring control, theta was proportional to I na, theta proportional to I na. That means according to the proportional, that is even if that is in previous case theta proportional to I, that means the deflection angle theta is directly proportional to a quantity, not proportional to tan, sin and all, right? It is proportional to that, theta proportional to I, which means the deflection angle is proportional to what? Is proportional to what? The I. But now at balance and steady state condition, this TD will be equal to TC, my dear. TD we know that TD proportional to I na. So here the theta proportional, sin theta proportional to I will happen here. Sin theta proportional to I will happen here. Okay, sin theta proportional to I will happen here, so that current will not be, or the scale will not be linear. But in the case of here, it is linear. It is a linear scale. That means in spring control, the scale is linear one, and in gravity control, the scale is not linear. The scale is not linear. Okay. Next type of damping torque. type of damping torque. First one, eddy current damping. Air friction damping. And third one, fluid friction damping. Fluid friction damping. So there are three types of main dampings. First one, air friction damping, fluid friction damping, and eddy current damping. Let's see one by one. First, air friction damping idea. First, let's see air friction damping. Draw this figure. Same idea. I already told you what was the function of a damping torque, my dear. What was the function of a damping torque? In order to suppress the damping, correct? In order to suppress the oscillations, we are using damping torque, correct? So here, see, the pointer started. It again come to here, and at TC, TD equal to TC, it will stop here definitely. We know that it will stop here. At the time of stopping, it will slightly oscillate. That oscillation you have to suppress. That is why you are using damping. So, and this, how the suppression here you provided me, here it contains a chamber, my dear. Air contained chamber is there. So, when the pointer moves downward direction, suppose the pointer is moving this direction, the aluminum frame will move like this. This mechanism will be adjusted in such a manner that if it is moving towards rightward, towards this positive direction, means it will move from left to right. So that what happened, the pointer come here and it move here. It start oscillation means nothing but a small comeback. A small try to come back is called the oscillation. Am I correct? Suppose a pointer is here, it's move here, it attend here. Oscillation means a small try to come back, that is called the oscillation. When the pointer try to come back means it is air tighten. This releasing is very easily you can release, but tightening is not, you need some force, right? So that extra force you required, that will cancel the backward direction of the pointer, so that the oscillation will not be there. You imagine, okay, it's releasing, suppose you have to come back, the force you should apply here, that means air resistance will be here, because air expands now inside it, the air has to compress, then only it will come back. So that compress now, there will be an opposing force by the compressed air, so that the pointer will not come back. Will not come back in the sense not providing the control torque, my dear. It will not oscillate. A small comeback, I already told you now, it's a small comeback. Try to small comeback is called the what? Oscillation. It's a try to small comeback is called the oscillation. So that oscillation will not be there. That is called the air friction damping. Is it clear? Is it clear? Is it clear, my dears? So in PMMC, that will accept. Okay, that is the air friction damping. Next, instead of using the air, we use fluid. Then it is called a fluid friction damping. There is no much change. Fluid friction damping means instead of this air we will use some type of fluid, then it is called fluid friction damping. Or we are using, this is also a type of fluid friction damping. Suppose you insert, here is some fluid, there you inserted a moving mechanism. There you inserted a moving mechanism means what happened? It will not move due to the friction of the fluid. It will not oscillate due to the friction of the fluid. Then that type of damping is called the fluid friction. You just remember this name, my dear. No need to deeply focus. Okay. Next is eddy current damping. You just understand the concept, that's all. Okay. And you have to note one thing, fluid friction damping is, yes, that we will take in at the time of instrument specifically, I will take that. So next, eddy current damping. Listen, my dears, listen. Eddy current damping means the moving system, my dear, moving system. The moving system is under the field, under the field of a permanent magnet. So first of all, this eddy current damping, it will be under the field of this permanent magnet. This will be a field of permanent magnet. So what happened means, suppose this is the aluminium frame. Suppose this is the aluminium frame. Aluminium frame. Okay. So what happened, my dears? If the pointer is oscillating at its initial final position, not initial, its final position, this piece, this aluminium frame, these also start oscillating. These also start oscillating. So due to this oscillation, there will be an induced EMF due to this presence of magnet. You know that if a conductor is moving nearby a magnet, definitely there will be an induced EMF. So like that here also, if it is oscillating, here also there will be an induced EMF. Due to Lenz's law, that induced EMF will always try to oppose the cause. Due to Lenz's law, it always opposes the Lenz's law, it always opposes the cause which is producing the induced EMF. So that there will be an eddy current. That eddy current will always oppose the cause. Here the cause is nothing but, my dear, the oscillation. So it itself can damp the oscillation. It itself can damp the oscillation. That's all. It's that much simple, no need to focus very much. Okay, that's all. Okay. So you know that this permanent magnet is nothing but alnico. Alnico is used as the permanent aluminium, nickel, cobalt, a combination of alloy of alnico is used as the permanent magnet. Okay. And next you have to see PMMC instruments. Okay, it's a big session. So that's all for today, my dears. Let's meet again tomorrow with a new session. Okay, so thank you so much.